just like at a convenience store that has a shoplifting problem, if I just leave the cameras on all the time, then when somebody picks something up and takes it out without paying, I'll be able to look through all the film and identify the person right in the midst of executing the event. That's what tracing all the time would be like. Except it's hard to go back and look through the mountains of data that, and Andy, yes, and Snapper. Yeah, exactly. And I'm not saying that these tools aren't useful. I mean, they absolutely are, and they're smartly designed, and they're a brilliant idea. But I want to propose to you that they're kind of founded on this vestige of an assumption that tracing is too expensive, therefore we can't do it, therefore we need surrogate things to do instead. So what I'd like to do today is talk about the case for database-wide tracing. I'm going to do it in the form of two stories. And one story is going to be 90% of our time, and the other story is going to be really quick. But I'd like you to see them both. And by the end of this, hopefully you're going to be able to look people in the eye and go, no, it's not a crazy idea to trace a whole database, even for a really long time. So that's the run-up. Let's get started. Let's see what I got here. So story number one is a story about an application that had intermittent timeouts. And I'll give you some background. The application that was having a problem is an airport operating, it's basically the airport OS. When you walk into an airport and you see the big monitors that say, here's where all the flights are, and here's where all the gates are, or here's the flight numbers and baggage claim. All that stuff is run in this story by an Oracle database for this busy airport. Now, the airport, as you can see on the slide, did about 100,000 transactions per hour, and they were experiencing about 10 timeouts per hour. Now, a timeout is when the application server makes a request to the database, and the database takes more than 5 seconds to respond. Now, if you do the math, there's a bunch of nines. I'm not going to try to do the math in front of you, but I think there's like 4 nines worth of goodness here. If I've got 100,000 things and all but 10 of them succeed, that's a lot of nines of success. But the problem is, every one of these 10 events that happen in an hour requires that an agent gets involved and tries to explain to a really unhappy passenger why the person's luggage went to Boston instead of Austin. So they're expensive, these timeouts. So the airport that was having this problem had labored for months without being able to solve the problem. And that's when they contacted us, and we put the following plan together. So the plan was, we'll trace everything for an hour, we'll catch these 10 timeouts, and then we'll find out the 4 basic questions about performance. We'll answer the question, how long did it take when a customer experienced a transaction? How long did that experience take? Why did it take the time that it did? What if we change this? What if we change that? How is that going to affect the response time? And then what else? So it's often an iterative loop. We'll either ask the what else question about, well, we made this thing that we looked at faster. Is that faster enough? And if the answer is no, we need to make it even faster. Then that's a loop of, all right, we're going to say, well, how long does it take now? It takes less time now than it did, but it's still not good enough. Why does it take the time it does? What if we change this? What if we change that? Sometimes the what else is, nope, this transaction's good. Let's go on to the second most important transaction for the business. So that's this little loop through what I call the 4 fundamental questions of performance analysis. How long, why, what if, and what else? So we did that. We actually convinced the airport to, and when I say we, the we is my team from Method R and the vendor of the software that is the airport operating system that was having a problem. So the airport contacted their software vendor contacted us. So it's kind of a triangular project where we've got the ISV, us, and the ultimate customer. So the ISV, independent software vendor, convinced their customer to trace for an hour. And what happened was they generated 67 trace files. That's 263 megabytes of data that was generated over the course of an hour. That's nearly 5 million lines of trace data. And it was about 90,000 transactions. Now, the best news on this whole page is they had 5 timeouts. Now, why is that awesome? Well, it's awesome for two reasons. Number one is you don't want to trace and not have a bad thing happen during the trace. Because at the end of that, you're like, oh, woohoo, congratulations, you had the world's greatest hour. But now we're stuck with, we need more diagnostic data. We'll have to do this again. So it's great news that we got 5 timeouts. It's even better news we got 5 instead of 10. Because remember, everybody, when they first hear, yeah, we're going to trace everything, they're like, oh my God, won't that cost too much? Well, apparently not, because if you're accustomed to getting 10 timeouts per hour, and with tracing turned on, you only got 5, well, double woohoo. So that was the best news of all. But somehow the airport knew that one of the transactions took 9.5 seconds. So that's the evidence we went in with. Now, there's a complication in the data because they use a technology called connection pooling, which means that they fire up some Oracle processes, and then those processes basically get shared among these application server database requests. So every trace file contains data from many Oracle sessions, and therefore it's an extra step to isolate these user experiences. Because see, what we're going to have at the end of the day is we're going to have this trace file for 67 different connections. And we're going to have to figure out, all right, where in this data are the things that people felt? So how do we identify these experience bottlenecks? And this brings us to a thing that Nancy mentioned a couple of weeks ago called the Oceans, Islands, Rivers algorithm. And here's a picture of Oceans, Islands, Rivers. It's kind of inspired by a map of islands. And you can see down here in this blue ocean, you can see a map of Hawaii where Hawaii is kind of the sand tan color. There's a little algorithm that implements this Oceans, Islands, Rivers concept. And basically, I'm gonna walk you through what this looks like here in the blue data down below. So here's what the trace data looks like in the information that we collected from the airport. Line 101 is a SQLnet message from client that has a fairly longish duration. This is 1.2 seconds. And then there's some work being done, a parse, a wait, an exec, a wait. And by the way, some of the waits have to do with network round trips, network IO. So here you see a SQLnet message from client that's a short duration call compared to this really long duration call. And so the reason Oceans, Islands, Rivers is called what it's called is because a trace file kind of reminds me of islands of activity, right? The sandy color, just like the islands of Hawaii, kind of in the midst of these oceans of idleness. So the long SQLnet message from clients represent the oceans of idleness, and the short SQLnet message from clients represent the rivers of activity within these islands of activity. All right, so I've got some builds here. Let me show you. So the algorithm basically says that long SQLnet message from clients get this label as being an ocean, and an ocean is distinguishable by having its line number be negative. That's what the algorithm says. Then there's this activity that takes place within an island, and these all get the island ID of the opening command or the opening database call that started the island. So you'll notice that all of these parse, exec, wait, all these things that happen in the TAN area all have the same island ID. And that island ID is the line number of the first action that happened after the ocean. So that's how this algorithm works. Then there's another negative, this is an ocean. And then there's going to be some more stuff that happens starting on line 108. And that's all going to get an island ID of 108. So now the cool thing about this algorithm is that if you can use a tool that recognizes the algorithm, you can actually group by island ID. And guess what you get? You get a report that shows the experiences that people felt. Now, folks, I am not exaggerating. When we got the trace data and we ran, so this is a report that comes from a software product called MethodR Workbench, which is how we make our living at MethodR. This report took, at the time, it took about a minute to run. You're going to see shortly, it only takes a few seconds to run now. We've made things faster. But what this report shows is everything the users felt. And it just, when we got this, when I got the 67 trace files, I'm like, oh crap, there's 67 trace files. That's so many. Now I can deal with 5,000 and it doesn't bother me. But when I ran this report and saw these, look at what we've got. We've got 5 lines in bold that are more than 5 seconds, not 6, just 5, just like they told us. And one of them took 9.5 seconds, just like they told us. Guys, I had tears coming off my cheeks when I saw this. And the data is just perfect. The data is just perfect. So we get this. What does that mean? That means that in this file, GXL aura 131.168.trc, starting at line number 145010, this is an island ID, as you can see in the label. There is an island of activity that took 9.44 seconds. All right. So it'd be nice to go figure out what's in there. So let's see. Here's the next step. We want to isolate the experience by cropping. And I use the term crop just like I would use it in Photoshop, the trace file. So here's how it works. Here's a picture of my lovely daughter about 3 years ago playing volleyball. And I love the picture. I love Jenna and I love all the other folks that are in the picture too, but I really just want to see Catherine. So what do? I crop the photo. So I execute an operation upon the original that results in just the thing I want to isolate. And that's exactly what we do to the trace file that has all this information about the 9.4 second transaction that timed out. Because in that trace file, there's lots of other lines too that don't have anything to do with the stuff that I actually want to see. So this GXL 131.168 file has 184,000 lines in it, but the lines where island ID is equal to 145010 plus a few others, there's only 504 lines I'm really interested in. So that's the goal. That's what we want to do. So what we get when we do that is this. So you might notice here's the 9.5 seconds and it's 9.474, not 9.44 as we originally thought, because this tool is more accurate at being able to basically calculate all of the timings that are missing inside of a trace file. So this is the real number, 9.474387 seconds. And nobody had any idea about this. It's a row lock. It's an 8-second long row lock. Nobody had a clue. And I'll show you why. Now, the funny thing is, all right, row lock. So we had 5 timeouts. I bet the other 4 timeouts are row locks too, right? Who wouldn't kind of naturally think that was the right question to ask? And it is. It's just not safe to assume that it is, because guess what? It's not. The second timeout on that list, that was a 7.5 second transaction, had a 7.5 second log file sync. All right, we probably all know what log file sync means. And I'm not trying to solve the problem right now. I'm just trying to tell you the story of what kind of data we can see. But the questions are piling up. Why is there a lock? Why is the log writer causing a problem? Is it the log writer? Is it maybe the system CPU saturated and the log writer can't get its next cycle because it's paged out? And all these questions I realize are mounting up. What about the third one? Is it an NQ or a log file sync? Yeah, the third one's a log file sync also. That's interesting. The fourth one happened to be a read call. Huh? A 5.5 second single block read call. Let that sink in. A 5.5 second single block read. Okay. Interesting. Now the fifth timeout, a log writer again. So what we got? 3 log writers, a read call, and an NQ. So cool. We've got trace data for all this. And I'm not going to solve the problem in front of you. But one thing we can do, because we have all this detailed trace data, is we can lay out timelines, for example, and we can see, oh, okay, the row lock contention happened at 1329, 43 through 1329.52. So that really doesn't correspond to any of these other times. You might notice I'm sorting by start time here. But the log file sync and the DB file sequential read, they kind of happened at the same time, within the same 15 milliseconds of each other. So these two are probably related. These 2 log file syncs, they happen within like 4 milliseconds of each other, 40, I guess, milliseconds of each other. So these are probably related. And basically the log file sync, all 3 log file syncs and the DB file sequential read all had to do with an IO subsystem that was having a problem. And of course, after we proved that the IO subsystem's having a problem, 4 or 5 people came out of the woodwork and said, oh, I told you that it was an IO subsystem problem. But nobody believed them, because look at what the data showed. this is what you get. Basically, I'm being unfair. Hopefully not ridiculously unfair, but this is the kind of data they were looking at. And this is the kind of stuff that you'll see in your brain when you look at AWR. You'll say, okay, we spent the vast majority of our DB time executing, 93.1% of our time. Lots of CPU time in that exec stuff. And then we had some log file sync. Well, who doesn't have log file sync every once in a while? The average log file sync is only 20 milliseconds. That's not a bad, it's not horrific. DB file sequential read. The average read duration is 9 milliseconds. It might be a little high. But it's not ridiculous. It's not preposterous. It's not, I'm going to go into battle and fight DB file sequential read durations over the data we're looking at here. This TXLock row contention thing, there's 10 total seconds out of like a half hour of data, and there was only 10 seconds of row locks. That's not a big deal. What you can't tell, though, from looking at this data is the skew of how these things conspire to make experiences miserable. And you can't prove misery from data that looks like the data that I'm showing you here. So that's the thing. So let me recap this. I want to show you the actual demo. I want to show you the actual steps of what it took to do this thing. So we had an intermittent performance problem. Only 0.01% of transactions were timing out, but they were expensive when they did. Months of not knowing why. Finally looked at the right thing. They traced everything. There was no perceptible performance intrusion, degradation by the trace. By the way, we've had clients that use tools like Dynatrace, for example. And Dynatrace is a very precise, I will measure all your transactions the way your users feel it kind of a tool. And we've even, with a Dynatrace trace, we've been able to prove that if you trace correctly, and that is basically level 8, waits equal true, binds equal false, you're not going to see enough performance intrusion that anybody will notice. So let me go do the exciting thing. I'm going to actually minimize this and show you some stuff. So this is MethodR Workbench. And the way this thing works is you drag trace files into the top files panel, and then you've got these actions you can execute on the side here. So I'm going to drag in, I've got a trace files directory that you can see has, looks like 74 items in it, which I'm not sure why it's 74 because I thought it was 67 or something. But what I'm going to do is I'm going to drag that directory into the MethodR Workbench. And what I'm not going to drop it yet. What I want you to look at is right about here, there's a status indicator that shows how many files have been processed so far. So we're going to drop in 264 megs of trace data. And then you can see all these little progress bars light up, and ta-da, it's over. These files are all loaded. Normally, if I weren't in a connection pooling environment, I would click on one of these durations and it's going to open up a browser window, hopefully that browser window, with data about that particular transaction. But we don't have a one-to-one mapping between transactions and trace files here because we're using connection pooling. So it's not really a very useful thing to do to click this duration because this doesn't represent somebody's experience. So what I want to do is show you that report of people's experiences. And if I go down here and type island, it reduces the list to just 4 things we can do. And what I want to do is duration by island ID is what I want to see. So I want to see that report over all these files. So I checked here to select all the files. And then when I click on duration by island ID, it says, okay, here's the command I'm going to run. It's a Mr. Skew command. And when I run this, it's going to ask me, what think time do you want to use? Now, I rehearsed, so this is the think time I want to use. If you're curious about why that's the magic number, it takes about 3 minutes to figure it out. But with that number, let me go ahead and click OK. And we've got 1, 2, 3, 4, 5. About 5 seconds, we have this report that shows the 5 timeouts. It's exactly what I showed you in the slide. So here are the 5 timeouts. One of them took 9.5 seconds. And you remember the file name, line number. And this line number here is the starting line of the trace file where that 9.447247 second experience lives. So let me do 2 things. I'm going to copy this number here, this 145010. I'm going to put that in my paste buffer. I'm going to come up here because now I really only care about one file for this part of my analysis. And I'm going to type in 131168, and it's going to leave me just one file in the list of files that match that criterion. And what I'm going to do now is I'm going to run this command called crop by island ID for a given island ID value. That's going to call forth this more complicated Mr. Crop, which is our cropping tool, which is going to say, I want you to create an output directory. I want you to do all this stuff. You don't have to think about it. You're just going to have to answer the question, what think time and what island ID. So let me go ahead and click that. And what I want you to notice is when I run this, it's going to ask me two questions. And again, I rehearsed, so it remembers the last numbers I used, but normally I would paste in the value 145010, which comes from right here. And then when I do this, I want you to pay a little bit of attention to what happens up here in my Finder window. I'm going to click that. And you might notice there's a new directory that got created. And that directory is called GXL aura _131168. And that's because there is this in the format string for the OFile parameter. But if I open this directory, I can see that there's a file called GXL aura 131168-145010. This is the island starting at line 0 at 145010. If I drag that into the files pane, I will see the reports of exactly why this thing took 9.47 seconds. And this was the NQ, you might remember. And if I click on this, I can see, okay, this NQ is associated with this update statement. And as soon as we mentioned it, the developer of the application said, yes, there's an opportunity between an update and a commit for if something, for example, like a long IO were to take place, I would hold the lock too long because there's code between the update and the commit, and the update and the commit in the app should be really close together. So, as soon as we got into the, I found your problem, the diagnostic and repair phase of this project didn't take very long. But folks, basically, getting the word on, so, okay, what's the second timeout? Well, it's this file 110636, 110636. Okay, it's that file there. And it's what line number? It's 9468. So I'll run this again and I'll type in 9468. You'll see another directory gets formed. I'll drag it over. It opens up. Okay, here's your 7 point. You see how easy it is to like mess around with 67 trace files? It's just like, but you can't do it with tkprof is the thing. So my theory is the reason that people don't use trace data at this level is because they don't have the tools to deal with all the data that would be generated if they did. And they also labor under this misapprehension from 1989 that you can't trace a whole system. And back then you kind of couldn't because IO subsystems weren't what they are today. But if you study up and don't trace binds, because there's a risk that if you trace binds that your trace will take a long time, then you can actually trace a whole database. Story number 2 is a nightly batch job that was taking longer than its window was supposed to allow. So they were having to actually pay their customers a cash rebate because they were failing to meet their service level agreement. One of the things that occurred to us during this project, helping these guys, was, well, we're going to need to trace your nightly batch because we don't have any idea which part of your batch is causing the biggest problem. And so this graph actually comes from Microsoft Excel after having loaded, there we go, after having loaded a bunch of files, which kind of look like this, and you notice that there's a start and finished column in the data. Well, we have an exporter, it's actually this guy here, that will actually take the data from the top panel and print it out in a nice columnar format if you want to copy and paste it into a text file. Or you can, if I type Excel, it will though. So details by file for plotting in Excel. And if I select that, you can see it'll do a CSV export of the data in the top panel. Well, realize the started and finished is for each trace file, not the M time of the trace file, but the time that's actually in the data that says, here's when this transaction began and here's when this transaction ended. So if we take the data from those two columns, it's actually pretty easy to make a Gantt chart that looks like this. And when you have a, and by the way, I'll just, for the slide in the recording, here's how you do it. But when we get a Gantt chart like this, the interesting thing is to notice a gap like that, to say, what in the world is going on? The database isn't doing work on this kind of thread that you can see. It's like it's processing SQL, right? The time is advancing from left to right. And then there's a huge gap where the database isn't doing anything regarding this transaction. And we asked them, what's going on between here and here? And they go, well, how would I know what here and here is? Well, we can open this trace file and see the last SQL in it. We can open this trace file and see the first SQL in it, because all you have to do is hover in Excel and you see the names of the files. Then we can go, okay, what happens between this SQL statement and that SQL statement? And they go, oh, that's easy. It's this thing, then this SAP data access thing we're running. Data services, I think is what it was called. And we know exactly where that is. And again, people are kind of rushing to, I knew exactly what that problem was. It was number 27 on our list of things to check. And the problem is, well, you're never going to get to number 27. But so a guy kind of crawled off and behind the scenes, and 2 hours later, he came back and said, yeah, I think I fixed that. There were like 18 places where that was happening. There was some caching parameter in the SAP data services product, had nothing to do with Oracle. There was no Oracle database problem at all. No parameter needed to be changed. No code needed to be changed. It was totally an SAP data services problem, but we found it using Oracle trace data. And by the way, this is the company that used Dynatrace. So they proved that nobody had noticed any kind of a performance degradation. Folks, I'm going to sign off. We'll see you next week. Thanks so much for your time.